The James Webb Space Telescope is the most delayed in the history of telescopes. It is also the most expensive. However, these two attributes have only increased expectations for the observation station as it gets nearer to start delivering the goods. It will uncover many of the universe's secrets, but one of the discoveries stands out because it changes everything: the warp bubble. What is the warp bubble and how will the James Webb Space Telescope help discover it? In this video, we dive into how the James Webb Space Telescope's insane warp bubble discovery will change everything. The James Webb Space Telescope, or JWST, is an amazing and novel piece of engineering. It required lots of ingenuity during the design, fabrication, assembling, and most importantly, launch. The NASA team and their partners had to be extra careful because, unlike the Hubble for instance, they got only one chance to launch the JWST with all its complexities. If anything went wrong, it means the mission failed. It means the loss of tens of billions of dollars and countless working hours and sweat. Everything just had to work because due to its location, there was nothing they could do after sending it off. The JWST now is in orbit 1 million miles away, so far out in space that NASA can't send engineers to fix any issue. The Hubble is much closer, orbiting the Earth at 547 kilometers, and astronauts have paid it a visit to correct some things. But for the JWST, not even refueling is certain at the moment. Unless NASA comes up with the technology for a spacecraft to go all the way and top up the fuel, the JWST will be abandoned after running out of its fuel supply. The orbit the JWST occupies is unstable and it will require constant course corrections. That is where most of the fuel will go. However, that is not happening soon, as NASA estimates there is enough fuel to run the JWST for about 20 years. So we have 2 decades of insane cosmic discoveries ahead of us. The JWST is a collaborative effort between NASA, the European Space Agency (ESA), and the Canadian Space Agency (CSA). It is an infrared telescope that can peer further away into space and further into the past than any previous telescope. The engineers chose infrared for several reasons. First off, infrared light can pass through cosmic dust without scattering to the same extent as visible light. The second reason is the phenomenon referred to as redshift, which means that as the universe expands, light is stretched from visible wavelengths to the infrared spectrum. As such, the telescope can see more distant destinations. And because of the immense size of the universe, redshifting allows us to see into the past, 13.5 billion years to be precise. At its location, it will hide in the Earth's shadow to minimize exposure to heat from the trio of the Sun, Earth, and Moon. This protection from heat is critical, so critical that NASA designed a special shield made of 5 layers made from a special material. Each layer was the size of a standard tennis court and it had to be folded up or the telescope wouldn't fit on the launch vehicle. But the shields had to be unfurled and precisely positioned to align or they won't work at all. The goal was to prevent interference with the heat-sensitive components on board. The primary mirror of the JWST was the biggest of any space telescope, and it too had to be, you guessed it, folded for the launch. NASA had this in mind when it designed the mirror to be made up of 18 different hexagonal segments and 6.5 meters in diameter altogether. However, while larger than the Hubble, the JWST is actually lighter. It weighed 14,300 pounds on Earth, while the older telescope weighed a whopping 24,500 pounds. At the moment, NASA engineers are working on the 4th stage of the long process to align the James Webb Space Telescope mirrors, according to a new statement from the agency. The observatory's near-infrared spectrograph (NIRSPEC) instrument has finished initial checkout, and its 3 key mechanisms have successfully been characterized, the statement noted. The instrument will allow Webb to study the fingerprint of light of up to 100 galaxies at a time, giving scientists crucial information about mass, temperature, and chemical composition at the same time. Earlier, the team corrected the positions of Webb's primary mirror segments and updated the alignment of the secondary mirror to bring the 18 individual images into focus. They then stacked the 18 images to produce one unified image. As things are, we are several months away from the JWST running at full speed, and that is when all the fun begins. Apart from looking back in time to see when the stars were newly formed, the observation station will help in hunting for exoplanets, a very hard process with the currently available instruments. Exoplanets are planets outside our solar system. They are so far away that imaging them is hard. In addition to studying planets outside our solar system, JWST will be able to observe our home planetary system. Its great sensitivity will enable the identification and characterization of comets and other icy bodies in the solar system's outermost regions. In such a remote location, these objects are largely unchanged since their formation and may contain clues to the origins of Earth, particularly the source of its water, which may be the result of bombardment by such bodies early in its lifetime. However, few discoveries made by the JWST will come close to the warp bubble because it is going to change everything. Let us start with what a warp bubble is. This is a pretty complicated subject that requires a lot of maths knowledge for a detailed understanding, but we will make do with a basic definition. A warp bubble is a bit of space that is contracted in the front and expanded in the back. The contraction and expansion theoretically pushes the bubble and its contents forward at speeds surpassing the speed of light without ever violating the laws of physics, because when you travel using a warp bubble, you are actually not technically traveling faster than light, you are only surfing a bubble of condensed space. Why is there so much hype around warp bubbles? That is because they eliminate a major problem of faster than light travel: time dilation. What does this mean? Let us say you did manage to travel faster than light. Everything else outside of your craft would speed up, meaning that the 3-hour tour you took to a nice tropical planet could have equated to years of time passing on Earth. Put simply, if you plan to move faster than light while following the known laws of physics, you would better say goodbye to everything you've ever loved before heading out. However, warp bubbles get around this problem because the space inside the bubble remains unaffected. So an hour of travel that you spend traveling at warp speed would mean that only an hour passed for everyone else not currently in your warp bubble. What are the real-life implications of warp bubbles? Well, let us take a look at the closest star to Earth, Proxima Centauri. It is about 4.25 light-years away, which is about 25 trillion miles or 40 trillion kilometers. The fastest ever spacecraft, the Parker Solar Probe, will reach a top speed of 450,000 miles per hour. This is very fast because it will take just 20 seconds to go from Los Angeles to New York City at that speed. But if you head for Proxima Centauri at that speed, it would take you about 6,633 years to reach your destination. But with warp bubbles, you can theoretically get to Alpha Centauri in a month, as measured by clocks on the spacecraft and clocks in mission control. The sensation of riding in a warp bubble is the floor behind you being created out of nothing and in front of you being destroyed, moving you along. Warp bubbles were long the domain of science fiction until theoretical physicist Miguel Alcubierre came along and theorized his Alcubierre warp drive in 1994, which maintained general relativity while allowing for faster-than-light travel. Alcubierre's warp drive would work by creating a bubble of flat spacetime around the spaceship and curving spacetime around that bubble to reduce distances. The warp drive would require either negative mass, a theorized type of matter, or a ring of negative energy density to work. But since physicists have never observed negative mass, we are left with negative energy as the only option. To create negative energy, a warp drive would use a huge amount of mass to create an imbalance between particles and antiparticles. For example, if an electron and an anti-electron appear near the warp drive, one of the particles will get trapped by the mass, and this results in an imbalance. This imbalance results in negative energy density. Alcubierre's warp drive would use this negative energy to create the space-time bubble. But for a warp drive to generate enough negative energy, you would need a lot of matter. Alcubierre estimated that a warp drive with a 100-meter bubble would require the mass of the entire visible universe. Sounds like a no-go area. Well, in 1999, physicist Chris Vandenbroek showed that expanding the volume inside the bubble but keeping the surface area constant would reduce the energy requirement significantly to just about the mass of the Sun. This is a significant drop in the requirement, but for practical purposes, where do we get the mass of the Sun to expend on a single trip? But that does not mean all hope is lost, because we might be able to do away with these prohibitive requirements, according to research by physicist Eric Lentz. Lentz examined the assumptions leading to the negative energy requirements in Alcubierre's work. Like his colleague, Lentz began by analyzing space-time, modeling the multidimensional substance as a stack of very thin layers. He found that Alcubierre had only considered comparatively simple linear relationships between the equations for shifting one layer onto the next, but Lentz chose more complex hyperbolic relations which typically express rapidly changing quantities. This resulted in a different warp bubble than the one obtained by Alcubierre. Of course, Lentz's warp bubble still requires enormous amounts of mass and energy, but only positive amounts according to his calculations. Are you excited about warp bubbles? Let's hear what you think in the comments section below.